Alright, so now in this video we need to talk about wave speed. If waves send energy from one place to another, then we need to consider how fast that energy is moving. So we'll talk about the speed of a wave. And basically, as I said, it describes the distance a wave moves in a period of time. That's no different from the normal definition of speed that we've always had. Speed is distance divided by time. How far does something go in a certain amount of time? But it's interesting for a wave that the speed of a wave is specifically determined by the medium through which the wave is moving. So depending on what it's going through, that determines the speed. All right, so take a minute and write down this stuff. And in case you're sitting there wondering, okay, what does the word medium mean? Is that like the size of a drink you order at Taco Bell? Is that like in between, small and large? Well, medium in science just simply means the stuff the wave must travel through. So for instance, right now the sound of this video is traveling to your ears in the form of a sound wave, and that sound wave is moving through air that's between the speaker and your ear. And in this case, air is the medium that we're talking about. Okay, so different media, like I said, this can be air. We can talk about water. You can actually hear sounds underwater, but they sound differently. Some types of speed of waves can travel through outer space. It doesn't have to actually have matter in the medium to travel, and that's an interesting thing as well. Waves can travel through all different kinds of mediums. Earth and rock, bone, body tissues. When we talk about if you go have a sonogram, or sometimes some different types of therapy use different types of sound vibrations that can travel through your body. So the medium is just whatever the wave is moving through. And this is a very important equation for you to know. V equals F lambda. This is the equation that talks about or governs the speed of a wave. So the speed of a wave is dependent on the medium as well as the frequency and the wavelength of the wave. So write these down. And these variables are nothing different for the most part from what we've had before. We've had velocity. You know it's in meters per second. Still has to be, just like it always has been. But we have two new variables. One is frequency. And frequency is in hertz. Actually, frequency is not new, isn't it? We talked about it on the previous page. Frequency is in hertz. It's still the number of cycles per second. And then lambda is wavelength, as we've also had on the previous page. And wavelength is just a special kind of length. Any length or distance must be in meters. So velocity is the frequency multiplied by the wavelength. And this one can be one of those that you can use your handy dandy little triangle to figure out. So if you want to write out to the side here, draw a small triangle that looks like this, that says V equals F times lambda. You'll be asked to solve for any of these three variables, and if you don't know how to do algebra well, this might help you to do the triangle. All right, now let's just simply do some practice problems with these. So speed of a transverse wave in a string, it says, is 15 meters per second. If a source provides a disturbance that has a frequency of 5 hertz, what is its wavelength? I'm going to actually go back to the notes to work this for you. So transverse wave, we got to remember, is the type of wave that looks like this. It goes up and down, up and down. It's moving at a speed of 15 meters per second. So that's the rate that the energy is moving from one side to the other within the string. That's not the rate that the string is moving. Remember, the string doesn't move. If the source produces a disturbance that has a frequency of 5 hertz. So they come right out and tell you that this is frequency. But even if they don't say the word frequency, you should know that hertz is the unit for frequency. So as far as guess method is concerned, that's our F. That's one thing they give us. That's our V. That's another thing that they give us. And they want to know the wavelength that's lambda. All right. So V equals F lambda, and we can simply plug in what we know. V is 15, frequency is 5. They want to know the wavelength, and if we divide by 5, we simply get 3 meters for lambda. That means if the speed is traveling this fast and the disturbance, or say somebody is moving a string at the other end 5 times per second for a cycle, and that means that each wavelength, each successive wavelength, the distance from crest to crest or trough to trough, is going to be 3 meters long. Let's look at the next one. A wave has a frequency of 20 hertz, so there's our F, as it travels along a slinky. All right, we've talked about a slinky before. Slinkies can actually make both types of waves, but most common is the compression type of wave. That's what we think about usually with slinkies. If the distance between successive compressions is 0.4 meters, what's the speed of the wave? All right, well, I know that speed is V, and that's what they're looking for, but the distance between successive compressions. Well, if we look on the front of the notes, look up there. Remember that wavelength right here was the distance between successive compressions. You should probably have that definition written there. So I know that they are giving me lambda here. They're giving me the wavelength. V equals F lambda again. So the velocity equals the frequency 20 times the wavelength of 0.4 meters. And if you punch that into your calculator, you'll get 8 meters per second for the speed of the wave. All right. I want to let you do practice problem number 4. I want you to work it with the person sitting right next to you. Substitute, if you would, please pause the video and allow them to work on this problem until it looks like they've all kind of come to a stop. All right. Hopefully you've done this. Let's go ahead and move through it together. Frequency is 262 hertz. Wavelength lambda is 1.29. What's the speed? Well, V equals frequency times the wavelength, so that's 262 times 1.29, and that's simply punched into the calculator, and I get 337.98. I'm going to call that 338 meters per second. How long will it take the wave to travel the length of a football field? 91.4 meters. It's kind of an interesting question because not exactly like the ones that we've done here, the previous 3. How long? Well, I'm looking for time. You should have been able to figure that out. How long will it take it to travel the length of a football field? That's the distance, right? Well, it's the same wave we're talking about. And we just found the velocity of the wave. And there's an old equation from way back in the day that goes something like this. V equals d over t. And actually, it's not really an old equation because it's on your equation chart. Everybody pull out your equation chart and look in the back on the waves and optics section. And look what you have on number 46. V equals d over t. This is one of our equations that we're going to use when we talk about waves. This is the second occurrence. We saw it here, and we also saw it on the front. Where was it? V equals d over t, velocity. Same exact equation. Looks a little bit different, but it's the same thing. So this is easy to solve now because I know that the velocity was 338. The distance was 91.4 meters. No conversion necessary. That's already right. And I want the time. All right. Now remember what we do when we have a fraction equal to a fraction, especially when the variable we're looking for is in the denominator. You got to cross multiply and get a new equation. So I got 338t equals 91.4, and now I can divide by 338. And if I do that, I get 0.27, 0.27 seconds. So this wave, this sound wave, which has a frequency of 262 hertz, which, by the way, we'll talk about this when we get to sound, but the frequency of a sound wave determines its pitch. It's going this fast, which is pretty close to the speed of sound. In fact, preview of coming attractions, speed of sound in air, 340, 338. Across a football field, it takes little more than a quarter of a second to get there. And that's why, I don't know if you've ever done this, but I had this experience when I was a kid. I was watching a baseball game. Here's our baseball diamond, you know, first, second, third, home. And I was standing out here, outside of the outfield fence, and I was noticing that when players would hit the ball here at home plate and they would sail somewhere, it would take a while for the sound waves to reach me, and I would see them hit the ball way before I heard it. And you may already know this, but the reason is because there's two types of waves that were reaching me. Light waves were reaching my eyes, but I also had sound waves that were reaching my ears. And light travels faster than sound. Sound takes about 0.27 seconds to get there, whereas light will get there almost instantaneously, just a hair of a millisecond to get from here to my eyes. All right, let's do the fourth one. What's the period of the wave? Well, period, remember on the front side of the notes, the definition of period, capital T, is the time for one cycle. All right, and if we look at the period is 1 over frequency, so that's the equation that we need to use. And they gave us the frequency 262 hertz, so 1 over 262. And if we do that, you'll get a really, really small number, 0.0038. And that's in seconds, so it takes 0.0038 seconds to complete one cycle. That's because the frequency is relatively high. Just for kicks, I'm going to go ahead and convert this to milliseconds. To go from seconds to milliseconds, you have to move the decimal 3 places to the right. So that gives us 3.8 milliseconds for the period of a wave. So the time that is needed to complete one cycle for a typical sound wave is 3.8 milliseconds. And it changes based on, or depending on the frequency of the wave. And the last part of the notes that we need to talk about are standing waves. And this is the bottom part of the back page. A standing wave is something that occurs when two opposing waves combined and they result in a single non-moving wave. Okay, and I'll show you a video, or actually I'm going to post the video for the sub to show here in a minute, the video of a standing wave. But standing waves are often the resultant of a flexion of a wave back on itself. Now, standing waves are not easy to create, okay? And you see there in the picture on the bottom of your notes, the picture of a person that is moving a rope up and down that's attached to the wall. Just because you move a rope up and down doesn't mean you'll create a standing wave. You have to move the rope or the string at exactly the right frequency to create that wave. And I'll demonstrate that for you on another video as well. But they occur, they're also known as stationary waves. Did I put that on there? No, I didn't. You might want to write that as a note to yourself, that they are also known as stationary waves. Stationary means they're not moving. And it looks like that because it literally looks as if a wave is standing there and not moving from one side to the other, even though it is. Standing waves only occur when the amplitude and frequency of the two waves are identical. The amplitude and the frequency of the wave moving forward and the wave coming back are identical. All right, and as far as the parts of a standing wave, this is what you need to label on one of those pictures of standing waves. Probably the second one is the largest one that also has a node. But it's already labeled for you in terms of A's and N's, but the point is wherever the waves come together, the small parts, those are called nodes. And the larger parts where they kind of separate again, those are called the antinodes, parts of a standing wave. All right, so we labeled the nodes the antinodes. Node is the point where the combined wave doesn't move, and the antinode is the point where they have greatest displacement. It's the bump in the wave, in other words. All right, I need you to pay close attention to this problem, practice problem number 5. You will have one like this, and it can be kind of confusing. First of all, it says, what's the wavelength if this slinky is 12 meters long? It should say if and not of. A standing wave has 4 nodes and 3 antinodes. The first thing to do when you have a question about a standing wave is to draw a picture of it. 4 nodes, 3 antinodes, and if you draw a picture, it happens to look like this one here. And here you can see we have, actually there's a node here as well, but there are 1, 2, 3, 4 nodes, and 1, 2, 3 antinodes. So this is the standing wave that we're talking about. Could be a slinky, could be a rope, doesn't matter. What is the wavelength? What's the length of one wave if the slinky is 12 meters long? Now, I want to show you something, that this is actually 2 waves. In purple, I will draw the wave that is going forward to the wall. And then what happens is when it hits the wall, it actually reflects back on itself. And when it reflects back in the opposite configuration that it went into. So instead of going in as a crest, it comes out a trough. So now you have colored these 2 different waves, the one going forward in purple, the one coming back in green. All right? And if we just look at each wave separately, okay, because remember this is 2 waves, and I want to find the wavelength of the one specific wave. Okay, it's the same wave, it's just going there and back. So right now, if we just consider taking away the green, for instance, and let's just consider that it's the purple there. Remember that the wavelength is the distance from between successive parts of the wave. So it could be from antinode to antinode, could be from node to node on the wave, successive nodes. So really the easiest way to do it, let's just say that, is crest to crest or trough to trough. Since we only have one trough in this wave, we'll just say crest to crest. All right, and this slinky, it tells us, is 12 meters long. All right, now if we look at this, remember, let's just reason this out, that the wavelength, I'm just going to write it, the wavelength is the length from antinode to the next identical ID antinode. The length from the antinode to the next identical antinode. And you could also just put node as well. All right? As far as a standing wave, it's the distance from the antinode to the next identical antinode. In other words, it's not from one antinode to the next. This is only a half wavelength because this antinode is only there because of the other wave. It's the distance from one antinode to the next identical antinode. This part of the wave is identical to this part of the wave because the purple is in the trough, in the crest formation in both places. Now, this is going to be easier to explain if we take this wavelength and actually just move it over just a tad to where instead of from this antinode to this antinode, it'll actually go from this node to this node. So we just moved it to the left exactly the same amount. And now notice that within this wavelength, we have 3 nodes included in it, 1, 2, 3. And you have 2 antinodes, 1, 2 antinodes included in that wavelength. Okay, and the important thing to know here is ultimately I want to know how many wavelengths, the number of wavelengths in the thing, like I said, And so to get the number of wavelengths, what I really need to do is take the total number of nodes that I have and divide them by 3. Or you could also take the total number of antinodes you have, and you could divide those by 2. Since we have 2 antinodes per 1 wavelength and 3 nodes per 1 wavelength, that's how you can take that. Point being this: our entire wave has 1, 2, 3, 4 nodes, 3 antinodes. So the total number of wavelengths, so hashtag lambdas, number of wavelengths, equals the number of nodes divided by 3. Well, I got 4 nodes, and I could do antinodes as well. You'll get the same answer. 4 nodes, I'll just put 4, divided by 3, because I know there's 3 nodes per wavelength. That gives me 1.5 wavelengths in this wave. And just to prove it to you, I can do the same thing with antinodes. Take the number of antinodes, there are 3, divide it by 2 antinodes per wavelength, I still get 1.5 wavelengths. So in this 12 meters, including that 12 meters, is 1.5 wavelengths. And that's easier to see if we look at one strand individually. There's 1 wavelength from upswing node to upswing node, and then we have another half of a wave, 1.5 wavelengths. How do I find the actual wavelength? Well, that's a distance, and I need to divide the total distance by the number of wavelengths that we have. So my distance is 12 divided by 1.5 wavelengths. And 12 divided by 1.5 gives us a wavelength of 8 meters. A lot of stuff to figure out. Basically, you need to find the number of wavelengths. It's good to have these notes. And if I were you, I would just memorize one of these. Just either know that I need to take the total number of nodes and divide it by 3, or the total number of antinodes are divided by 2, or just look at the picture and you go up, down, up. There's 1 wave. Half of another one. There's 1.5 waves. If you can't figure that out, use the little formula. Total number of nodes divided by 3, or the total number of antinodes divided by 2 gives you the same number. I have 1.5 waves. And then you take the total distance of the standing wave and divide it by the number of waves, and it gives you the total wavelength.